So when you draw the ray diagrams, it's very easy to identify the positions of the object and the image. But what if we don't have a diagram with us? How do we measure the distances of the object and the image from the mirror? For that, we need to use something, and that something is called as the mirror formula. So this is the formula that we have, that is 1 by V plus 1 by U is equal to 1 by F. Now here, what is small v and what is small u? We already know what small f is, right? It is the focal length. But what is small v and what is small u? Let's try and understand. For that, we need to have a base diagram with us. Now we know we can place our object anywhere on this base diagram. Let's place the object over here, that is beyond C, and name our object AB. Now, to measure its distance from the mirror, from where do we measure? We should always measure distances from the pole of the mirror. So right now, the distance between the pole and the object, that is distance PA, is called as the object distance, and object distance is denoted by small letter u. So object distance is denoted by u. Similarly, let's try to test our knowledge. When we place the object beyond C, where is the image obtained? It is obtained between C and F. I hope you were able to answer this. So now we have the image between C and F, or F and C. So how do we measure its distance from the mirror? From the pole of the mirror. So PA dash right now is the distance of the image from the mirror, which is denoted by small letter V. So image distance is denoted by V, object distance is denoted by U. And we also know that small f is the focal length, that is the distance between the pole and the focus. So we have 1 by V, which is the image distance, plus 1 by U, which is the object distance, is equal to 1 upon F, which is the focal length. So now, this is the formula that we are supposed to derive. That means we are going to do the derivation of the formula for curved mirrors. So we are going to prove this. So to prove this, how do we start? We start by drawing the diagram and naming whatever we know. What do we know in this base diagram as of now? We know what is capital C, right? What is capital C? It is the center of curvature. So we write that. So here C is the center of curvature. What is capital F? It is nothing but the focus. So F is the focus. Now what we are going to do is we are going to place our object. So here we are placing our object AB, and we know that objects are always perpendicular to the principal axis. So here what is AB? AB is nothing but the height of the object. So we write that. AB, height of object. Now, we know that we have drawn ray diagrams. What do we do after placing the object? We apply rules, right? What is the first rule? That the incident ray should be parallel to the principal axis. Now, we can see that this ray is parallel to the principal axis and it is striking the mirror, right? It is striking the mirror at this point. Let us name this point as X. So this ray becomes ray BX, which is parallel to the principal axis, and it is striking the mirror at which point? At X. We are supposed to write that. So ray BX parallel to the principal axis strikes the mirror at X. Now we know that after reflection, it is going to pass through the focus. So let's pass it through the focus. Do not forget to draw the arrows, which are very, very, very important. Now, we know that we can apply two more rules. Let's apply the rule of center of curvature. We know that when the incident ray passes through the center of curvature, after reflection it traces the same path, right? So this ray is striking the mirror at this point. Here we named it as X, here we'll name it as Y. And we know after reflection it is going to travel back in the same direction, so we draw an arrow over here. And again we are supposed to write the same thing. So ray BY passing through C. Ray BY passing through C strikes the mirror at which point? At Y. Now we know at this particular point, the rays are meeting after reflection. That means at this point, the image is going to be formed. And we know it is a real and inverted image. So here we have named the image as A dash B dash. What is A dash B dash? Height of the image, right? So we write that. A dash B dash is the height of image. Now, what else do we know? We know the object distance, we know the image distance, and we know the focal length. And we know one more thing, that is the radius of curvature. That is what we are supposed to write. So let's see. We know that PA is the object distance, because object distance is the distance between the object and the pole of the mirror. So PA is equal to U, that is the object distance. So PA is equal to U. Now we know that image is formed over here, and this distance PA dash is the image distance. And what is image distance denoted by? V, right? So image distance is denoted by V. So PA dash is equal to V. Let's write that. PA dash is equal to V. Now the next thing. We know that focal length is nothing but the distance between the focus and the pole, that is PF is equal to small f. So we write PF is equal to small f. Now what is the radius of curvature? We know that radius of curvature is the distance between the pole and the center of curvature, right? And what is it denoted by? Capital R. So here we have PC is equal to capital R. So we write that PC is equal to R. But we also know for a fact that radius of curvature is nothing but twice the focal length, which is equal to 2f. So we write that PC is equal to R is equal to 2f. So this is the data that we have as of now. So this is how we start the derivation of formula for curved mirrors. So let's keep this data with us over here. So what do we need to prove? We need to prove the formula 1 by V plus 1 by U is equal to 1 by F. So in the formula we have V, we have U and we have F, and we also have the values of these terms, that is PA, PA dash and PF. But if you see the formula properly, the formula is 1 by V plus 1 by U is equal to 1 by F, which means here we have ratios and we have to prove ratios to be equal. So how do we do that? For that we have to use geometry, and in geometry we have learnt that we can prove the ratios to be equal by using similarity of triangles. That means the terms that we have, they should be a part of some triangles. Let's check whether the terms that we have, they form the part of any triangle. The first one is PA. Let's check whether PA forms a part of any triangle. PA, is it forming a part of any triangle? No, right? Then we have PA dash. Let's check that. PA dash, is it forming a part of any triangle? No again. Then we have PF. We have PF over here. Is it forming a part of any triangle? No, it's not. That means the terms that we have as of now are not forming a part of any triangle. That means we have to use something related to the object which forms a part of a triangle. For example, object height and image height, they are related to the object and the image, right? So we can use them and check whether they are forming a part of any triangle. So we have the object as AB over here and image as A dash B dash. Is AB forming a part of any triangle? Yes, I can see that. Triangle BAC, right? Similarly, A dash B dash is forming a part of a triangle B dash A dash C. So here we can see that the object height and the image height are indeed forming a part of triangle, and we can use these two triangles and we can prove their similarity in order to prove our formula. So we have these two triangles. Let's try and prove them similar. Now one of the easiest way to prove them is by using the AA criterion, right? For that we just need to prove two angles to be equal, right? So here I can already see one angle to be equal, that is angle BAC equal to angle B dash A dash and C. I can see one more pair of angles to be equal. Let's see that. Can you guess the reason for them to be equal? Simple, vertically opposite angles. So we already have two angles or two pair of angles to be equal, right? So here we can prove these two triangles to be similar, triangle BAC and triangle B dash A dash C. How? First of all, we have angle BAC equal to angle B dash A dash C. That is what we have written over here. And the reason for that is each 90 degrees. Now the next pair of angles you can see over here is BCA equal to angle B dash A dash C. So here, what is the reason? Vertically opposite angles. So we have proved the two triangles to be similar, triangle BAC similar to triangle B dash A dash C. Now, what is the reason for that? The reason is simply by AA criterion of similarity. So after proving the two triangles to be similar, now we have to write down the ratios of their corresponding sides. Let's start writing. So first of all, we'll have BA and B dash A dash. Can we write it as AB and A dash B dash? Absolutely. So we have AB upon A dash B dash. AB upon A dash B dash is equal to AC and A dash C. AC and A dash C. So we write AC upon A dash C. Now we also have the ratio of the third side, but we are simply ignoring it. Why? Because it is not required. The third ratio would be BC upon B dash C. BC upon B dash C, which is the part of the hypotenuse. It is neither forming the part of the object height and the image height, nor it is the part of the principal axis, so we simply ignore that. So here we need to write the reason now. The reason is corresponding sides of similar triangles, and we can keep this equation as equation number 1. Now, in this equation you can see on the left hand side we have AB upon A dash B dash. AB upon A dash B dash. Now these are the height of the object and the height of the image. But in the formula, do we have height of the object and height of the image? No, right? That means we'll have to eliminate the left hand side. How do we eliminate the left hand side? We'll have to find the value of left hand side. How do we find the value of left hand side? It is a ratio, right? That means we'll have to prove this ratio to be equal to some other ratio. And how do we do that? By simply proving two triangles to be similar. Now here we know that A dash B dash can form the part of this triangle as well. That is triangle B dash A dash F, right? Now we need to prove it similar to some other triangle. Can you see something similar over here? But this is not a triangle, right? So we need to do a construction over here. What we'll do is from point X, we'll draw a perpendicular at the point P dash. So draw XP dash perpendicular to PA. So here we have two triangles over here, or a pair of triangles. So the two triangles can be proved similar by AA criterion, that is each 90 degrees and vertically opposite angles. So the two triangles now are similar. So we write similarly on proving triangle XP dash F. XP dash F is similar to triangle B dash A dash F. B dash A dash F, right? So now we need to write its ratios. The ratios could be XP dash upon B dash A dash, which can also be written as P dash X upon A dash B dash is equal to P dash F upon A dash F. So now we can ignore the third side, as we already know. So this is equation number 2. So we have equation number 1 and equation number 2. If you see properly, on the left hand side in the denominator we have A dash B dash and A dash B dash. If you look in the numerator, we have AB and P dash X. Let's see that in the diagram. We have AB and P dash X, right? Can we find a relation between these two? If you see properly, they are of the same height because they both are perpendicular and they both are between the same set of parallel lines. So which means that AB is equal to P dash X, which is equation number 3. So from equation 1, 2 and 3, what we realize is that the left hand side is equal to left hand side, which means the right hand side would be equal to the right hand side, which means AC upon A dash C will be equal to P dash F upon A dash F. From where did we get this? From equations 1, 2 and 3. So this becomes our equation number 4. Now this is very important. If you see over here, we have P dash F. Where is P dash F in the diagram? It is over here, P dash F. Do we have the value of P dash F? If you see, we don't have the value of P dash F, we have the value of PF. So if somehow we can prove that P dash F is equal to PF, then our derivation becomes very simple. But how do we do that? To do that, what we need to understand is that the diagram that we have drawn or the derivation that we are doing are only for para-axial rays. Now you might think, what are para-axial rays? Para-axial rays are those rays which travel very close to the principal axis. For example, we have ray BX over here. This ray BX is a para-axial ray because it is traveling very close to the principal axis. And one more thing we have to keep in mind, which is very, very, very important, that the mirrors that we are dealing with have a very small aperture. Now what do you mean by aperture? Aperture means the total effective area. So these mirrors have a very small aperture. That means these mirrors are very, very small. Now, if these mirrors are very small, we know that these small mirrors are actually a part of a big spherical mirror. Now, if they are a part of a big spherical mirror and these mirrors are very small, then these mirrors appear. I'm not saying they are. I'm saying they appear to be like a plane mirror or as good as a plane mirror. That means if you talk about this line xp dash and if you talk about the line xp, or we can say segment xp, they are almost equal. Why did I say almost equal? Because this line, we are assuming it that it is a straight line. Why straight? Because it is a part of a straight, that is a plane mirror. So here, if these two lines are equal, we can say that point P and point P dash, they will coincide. So here what we are supposed to write is that if the rays are paraxial, then we can say that P dash coincides with P. And also we know that the mirror has a very small aperture. So if P dash F is equal to PF, and if we substitute this value in this equation, that is equation 5, in equation 4, what do we get? We get AC upon A dash C as it is. Instead of P dash F, what are we supposed to write? PF. So we have PF upon A dash F. Now this is the main equation that we have from 4 and 5. So now what we need to understand is, let us look at this particular segment, that is AC. Where is AC in the diagram? We have it over here, right? So AC is over here, so we write AC. Now one question to you. Is AC a part of a bigger segment? Yes it is. That is PA. So we write PA. Now in order to get AC, what do we have to subtract from PA? We have to subtract PC. So we have PA minus PC. That means AC is equal to PA minus PC. Do we have the value of PA? Yes, we do. That is U. So we write U minus PC. PC is nothing but 2F. So we write U minus 2F. So we have AC is equal to U minus 2F. Then we have A dash C. Let us see. Let us find out in the same way as we did for AC. We have A dash C over here. Is it a part of a bigger segment? Yes, it is. Which segment is that? That is PC. So we write PC minus what? Minus PA dash. So we have PC minus PA dash. Do we have the value of PC? Yes, that is 2F. So we write 2F minus PA dash. Where is PA dash? PA dash is over here, that is V. So we have 2F minus V. Then we have PF, that is also equal to small f. That means we are not supposed to write that right now. And we have A dash F. Where is A dash F? A dash F is over here. And we know it is a part of a bigger segment. What is that segment? That segment is PA dash. So we write PA dash minus what? Minus PF. So we have PA dash minus PF. So do we have the value of PA dash? Yes, that is small v. And we have the value of PF, that is nothing but small f. So we write small f. So these are the values that we have, and these are the values that we are supposed to use right now. Now, AC we have at the top, right? What is the value of AC? We are just substituting the values right now. So AC is U minus 2F, so we write U minus 2F. Then we have A dash C. A dash C is nothing but 2F minus V. Then we have PF as small f. And we have A dash F. We have A dash F over here, which is equal to V minus F. So now that we have substituted the values, let's keep this aside and focus on this equation. Now this is simple algebra. So here you can see what we have to do is we have to cross multiply. So we have to multiply U minus 2F into V minus F. So we write U minus 2F into V minus F, which will be equal to what? F into 2F minus V. So we write F into 2F minus V. Now on the left hand side, we have two brackets. That means we have to open the bracket first of all. So this first term into the entire bracket. So first of all, we have U into V, which becomes what? UV, right? So we write UV over here. Now U into F becomes UF. And what would be the sign? Minus sign. So we write minus UF. Lovely. Now we have 2F over here, but we have to write the sign, that is minus sign. So 2F into V becomes minus 2VF. So we write minus 2VF. Now minus into minus gives us plus. And 2F into F becomes 2F square. So we have plus 2F square. So this is the left hand side that we have done. Now on the right hand side, we have to open the bracket once again. So we have f into 2f. What is that? 2f square, right? Then we have f into v, which becomes vf or fv, and the sign should be a minus sign. So we have minus vf. Lovely. So now we have opened the bracket. Now let's observe the left hand side and the right hand side. Can anything get cancelled over here? Yes, right? Because plus 2f square and plus 2f square on the right hand side will get cancelled. Now after this, again we have to observe the equation. We have uv, we have minus uf, minus 2vf, and on that side we have vf. That means if you see, some terms have f in it. So what we are going to do is, we are going to keep all the terms that have f in them on one side. So uv remains as it is, and minus uf, minus 2vf goes to the right hand side. So we write uv as it is, minus uf goes to the right hand side, becomes plus uf. Minus 2vf goes to the right hand side, becomes plus 2vf, and minus vf remains as it is. So we have uv is equal to uf plus 2vf minus vf. Now uv remains as it is, uf remains as it is. Now here we have like terms, right? And we have different sign. That means we need to subtract over here. So plus 2vf minus vf gives us vf. So we have plus vf over here. Now observe the right hand side carefully. Can you see something common? Yes, I can. That is small f, right? So uv remains as it is, and here we have f common. So we write f as it is. Then what remains? U plus v. Now what we understand over here is that on the left hand side we have a product, and on the right hand side we have a product. That means we have two products equal. So whenever we have two products equal, we can form two equal ratios. That means here we have to form ratios. So let's try and form some ratio. Let's look at the formula. What do we want? We want 1 by f, right? We want 1 by f. That means f needs to be in the denominator. If we see the equation that we have f on the right hand side in the numerator. That means we can shift f to the left hand side in the denominator. So we do that. Now we know that u plus v will remain as it is. So we write u plus v. Now what do we want in the numerator? We want nothing. We want 1, right? So we have uv on the left hand side. So uv will shift to the right hand side in the denominator. Then what remains is nothing but 1. So we have 1 upon f is equal to u plus v upon uv. So we get 1 upon f, we have 1 upon f, right? Now we write 1 upon f as it is. On the right hand side you can see that we have the base, the denominator common. That means we can split the numerator. So we have u upon uv plus v upon uv. So u and u gets cancelled, v and v gets cancelled. What remains is 1 upon f equal to. Now here there's a possibility of making a mistake. You might forget there is 1 in the numerator. You have cancelled u, that means there is 1 in the numerator. So we have 1 upon v plus 1 upon u. So you can either keep the formula as it is, or you can shift it and make it as 1 by v plus 1 by u equal to 1 by f. So this completes the derivation of the formula for curved mirrors.
And yes, please do not forget to like, share, subscribe, and press the bell icon.